Hi, YouTube. My name is Nick, and today I want to present to you one of my little side projects that I've been working on a little bit on and off. Last time I presented it was maybe over a month ago. So I think it's very much time for a solid update because a ton has changed and the project has begun to take its final form. What am I talking about? Well, the project name is llamaMan. I have an article for it presenting it right here. So I have an article presenting all of the latest changes right here. But llamaMan is basically it's an application that allows you to proxy multiple llama.cpp instances for inference across multiple servers if you want that. I built it specifically for this purpose, but now since it's nearing its completion, it's gonna enter a maintenance state unless there's gonna be something really big and revolutionary, in which case I will consider adding in new features and stuff like that. Okay, so let's take a look at this thing. This is, your standard llama CPP or VLLM deployment. You have your PC or your home server or whatever, or you have a VM where you pass through hardware to it, and then on that host you run the inference engine, which in this case is llama CPP, VLLM, or whatever people use out there. And what happens in this scenario is your clients, they would send the request to the server, and the server would forward that request to the exposed port for your llama CPP instance. And your llama CPP instance is going to use your hardware resources to run that LLM model and provide a response back to your client. And this is, the most common way that people do these things. Now, there is another very common case besides this one. This is the simplest thing that most people would do at home usually, especially if maybe they have like just one host. But there is another situation where people, for example, might use Docker for maybe a production deployment. Maybe they have a couple of hosts where they want to deploy, the same type of thing. They want to have, continuity and consistency of their deployments. And this is that situation right here. We have, again, the inference, web UI, or a local agent for the client that you're working on. You might, again, have a server that's going to send the inference requests. This is your server that's going to host a Docker service. And within that Docker service, you're going to have your llama CPP or VLLM instance running. So via the Docker image, you pass through hardware to that instance. Then you maintain that Docker image with a Docker compose file or something else, and you have a consistent way of deploying things. Now, the problem with this is that whenever you want to swap out models, technically you would have to redeploy a container. And because GGML realized that because people would have to redeploy containers, to swap out images and so on and so forth, they very recently implemented an ini file configuration where you can specify like a few models that can swap in and out based on how they're requested. And this is very close to one of the features that llamaMan actually has. But let's see what the initial llamaMan implementation was. We're still not using llamaMan in this situation. The initial llamaMan implementation is a little bit more like this. Here's what happens. Your clients send their requests to the server. On your server, you have a Docker container, and inside that Docker container, you have llamaMan, which was built on top of the GGML llama CPP images. Then inside that container, llamaMan would be able to start one or multiple instances of llama CPP. So it would be able to proxy incoming requests based on the requested image to either of these instances living inside the container. In this situation, llamaMan used to track and manage process IDs for each of the llama CPP instances. Now, in this situation, llama CPP inst 0 could use the system RAM allocated to it by llamaMan and a particular GPU allocated to it. You could also pool GPUs to one instance. You could tell it, use all of my GPUs in a pool, as long as the llamaMan Docker container can see those GPUs, but you might want to also separate, one GPU per deployment, or one deployment gets two GPUs, one gets one, and so on and so forth. You can mix and match, the hardware capabilities. Inference engine runs inside a Docker container on host OS, okay? This is the base image. llamaMan was built on top of the llama CPP Docker image I already said this. Clients which are local or remote send requests to the host running llamaMan Docker instance managing one or more llama CPP instances with hardware distribution, LRU eviction, load balancing, and queue management. Queue management here is very important because you might have like two separate llama CPP instances running the same model. Each one gets a GPU, or one gets just one GPU and the other runs on CPU and RAM. And you could toggle on a setting which would basically tell llamaMan these two instances share essentially the same queue. So the queue would load balance between the two llama CPP instances. And we're already headed towards the direction of the final vision for the llamaMan project, which, by the way, I still haven't said it. llamaMan stands for Llama Manager. Then we have the thing that I already told you about. Hardware is distributed to the llamaMan container, which in turn can set limits and distribute resources to each internally managed llama CPP instance. And then llama CPP instances sharing the same model can share queues. This is the key feature. Now, the problem with this entire setup was that you would constantly get driver updates, newer llama CPP versions, because things are extremely dynamic. People are constantly updating everything. And it was a real hassle keeping track with all of the changes. And I was building fat images, PH fat, because llamaMan was sitting on top of, like, say, for example, the CUDA image was a few gigs. The ROCm image was like 7 or 10-ish gigs. So the container will take forever to build. It was a hassle to constantly keep track of what's going on. So the right decision in this situation was to decouple llamaMan from the llama CPP instances. So here's what I came up with. This is the exact same thing, but here we have llamaMan decoupled from the fat llama CPP image base. So since version 0.96, llamaMan now became a manager of Docker images. So let's take a look at the notes here. Clients, local or remote, send requests to hosts running llamaMan Docker instance managing one or more llama CPP containers. These are now containers with hardware distribution, LRU eviction, load balancing, queue management, and so on and so forth. So now these are Docker images. llamaMan manages and pulls and deletes the Docker images, which you can choose based on your hardware. llamaMan would essentially manage exclusively containers which are llama CPP Docker instances. llamaMan would be able to see your hardware, but now instead of directly assigning GPUs to a llama CPP instance running directly inside the llamaMan container, llamaMan would assign the hardware through the Docker API to the llama CPP container. Inference engine runs inside its dedicated Docker container on host OS. llamaMan image is independent and manages llama CPP containers and Docker images. llamaMan is aware of system hardware for resource monitoring and distribution for launching llama CPP Docker instances. llamaMan can dynamically change preset values which are not finalized at llama CPP container runtime. So for example, you might have certain values which are relative to the queue, which can be changed even while the llama CPP Docker image is running, since llamaMan proxies incoming requests to these instances. Llama CPP Docker instances sharing the same model can share queues. This was all fine and dandy, and this was essentially the proof of concept that this can be done. So the next thing, because llamaMan supports two types of storage backends, one is, directly through JSON files, and the other storage backend is through a database, which is MariaDB or MySQL. I decided now is the time to introduce clustering. So if you configure a storage backend to be the database, what you can do is essentially get to this type of situation. So maybe you have like a few PCs lying around at home. Some PCs are old, but they can still be used, believe it or not, for AI. Here's how clustering works. You can have just essentially this situation. You don't need to enable clustering, and clustering is not mandatory. This is still valid to this day. But if you have a second PC at home, or, a NAS where you can just slap in an extra GPU or something, you can keep your original llamaMan deployment, but then you can set up a database And you can then set up on your other machine, which might be even your desktop. If you're working all day and your desktop isn't doing anything, you take your original llamaMan instance, then you use your Docker Compose and you modify it a little bit. I'm going to show you what I mean here in just a second. And you deploy on a second server or third server or even fourth server. I've tested with 3 at a time at most. So I think that, it should be good with 4, maybe 5 if you have them. You connect them both to the same storage backend, which is the database, with a shared key. It's very important that each node has its own name, but the key needs to be shared between all nodes, right? In order for them to join a cluster and be able to talk to each other. And now what you can do is you can direct those clients to either this server or this server, and these servers are essentially interchangeable. You can manage each cluster node through every other cluster node. Each server can distribute hardware accordingly to each Docker container, and requests on the same node can share, if you have 2 instances of the same model, they can share the queue. But now if you have 2 instances across 2 nodes or more that share the same model or not, we're going to take a look at this in a little bit, they can share the same queue and process the same load. Why is all of this necessary? It's very simple. So if you have a limited hardware resource, right? Say, for example, you have 1 GPU. On my Unraid box, I have a 4060 Ti. If I batch request like 30 requests on that 4060, even though you can have CPU and RAM offload, the entire thing is gonna choke out, meaning that memory pressure increases since we now have to process n number of requests at a time. You're now generating fewer and fewer tokens. Quality of the generations drops significantly. It's not only the speed, it's also the quality. Add more GPUs to the system. If you give a model more GPUs, it would be more efficient at handling those multiple requests. But what if you can't do that? So you add another machine to this cluster. Now you have parallelism, where all of the setups possible up until this moment are still possible, but now you extend the capability to process multiple requests at a time. So clients, local or remote, send requests to any host running a llamaMan Docker instance, managing 1 or more llama.cpp containers with hardware distribution, LRU eviction, load balancing, and queue management. With clustering enabled, llamaMan instances across servers become aware of each other via the database backend right here and are able to share and balance queues. Clustering allows queues to be shared between shared models by model name, as well as a cluster group name or label. Using cluster group name or label also allows for different quants of the same model or models to share the same queue. Oops, I duplicated this one. Let me just, Then we have some cluster group members can be used as fallback or queue overflow if queues for primary members are full and requests keep coming in. Inference Engine runs inside its dedicated Docker container on host OS. This is the llama.cpp containers, okay? llamaMan image is independent and manages llama.cpp containers and Docker images, but with the addition that every host can manage every other host. llamaMan is aware of system hardware for resource monitoring and distribution for launching llama.cpp Docker instances. llamaMan can dynamically change preset values which are not finalized at llama.cpp container runtime. Request logging is global. llamaMan application management and maintenance jobs are also global. So we're going to take a look at what all of this means in practice right now. All right, so this is llamaMan running on my Unraid box. Now this node is already running in cluster mode. We can verify by just taking a look at the cluster tab. And we're going to take a look at what is required for a node to run in cluster mode. To do that, we're going to go in here and I'm just going to do a cat on Docker Compose. And in the Docker Compose on my Unraid box, we can see that for llamaMan, we have 3 primary variables which enable clustering. So this is the advertised URL for the unraid box. This is the address of the unraid box, and this is the port that llamaMan is running on. We have cluster enabled true, and this is the cluster secret that I told you about that needs to be enabled. And all of the nodes need to have this cluster secret shared between each other. Now, what is also required is llamaMan node name, which is now mandatory, a mandatory setting for every node that is deployed. It needs to be unique. If you're going to run a cluster, you cannot have, two separate nodes with the same name. The rest of the resources are pretty self-explanatory. If you want more info on how the deployment works, it hasn't really changed all that much since my last video. So I would recommend that you find the, in the video description, the last video where some of the options are explained in terms of how the container is set up. Also, take a look at the repository documentation. That's going to be very useful to figure things out. Here's what we're looking at. In here, we have like a bunch of containers. Okay. Now, for the demonstrational purposes of this video, I'm going to run GPT OSS 20B, and in here we can see this is our server that we're currently managing. We can see our GPU resources. We're gonna, if we have multiple GPUs on a system, these will be listed underneath, your server. So let's launch this model. It says preset loaded. Our other node is still offline. This is the Docker image that we're going to be using. We can manage Docker images in this page. 12 CPU threads, 20 gigs of RAM, max concurrent, 3 requests at a time that can be batch processed by the model. Now, for the sake of this video and for purely, demonstrational purposes, I'm just going to straight up go ahead and change this to 1 because this will allow me to better demonstrate how the system works. Then we have proxy sampling overrides. You can set overrides for incoming requests, for the llamaMan proxy, which for this model specifically will take on whatever settings you put in here. So basically, if you have a client that has their sampling overrides sent to the llamaMan proxy, if this is activated, the llamaMan proxy is going to discard those and take these values here instead. Okay. Then recently, since speculative decoding was implemented, and we have the draft MTP option for certain models that support this. This is a nice to have quick little toggle on and set a value type thing. The default value here is 2. And for other speculative decoding options, you can just disable this and just use the extra args thing right here. Okay, so here's the key part. If I had 2 GPUs or I wanted to deploy like one instance of this on GPU and one instance to run on system memory and GPU, I could, share queue with the same model, and both of these llama.cpp Docker images would run on my unraid box and they would share the same queue, kind of in a local type cluster, if you will. So I'm just going to go ahead and enable this right now and just basically launch. This is still max concurrent is 1, and idle timeout, I'm going to set this to 3 hours, and I'm just going to launch, collapse this, and we're just going to wait for the model to start up. We see that our queue is 0 out of 1, meaning that one request can be processed by this model at a time. All right, and the model is healthy. We can see the instance. We don't have any stats for it right now. And we can see the GPU load, is currently at 0 with a bunch of VRAM taken up. Now let's go ahead and just start a test. In the repository, I've included a cluster load test, which can be used in single deployments as well, without there actually being a cluster. So we just need to specify our model name, and it will send a request, for example, with the prompt, in this case, hi there, with a number of the request itself. And we're just looping through sending requests asynchronously. And then we wait for them, and the system logs how the requests were processed. Okay, just run this, and we can see that we have 1 active, and it just plows through all of them. These already completed. Okay, this was the most basic example of how queuing works, right? So now I'm going to open up my VS Code. Let's take a look at this Docker Compose and see what's going on. We're using the same database as with my unraid box. Now this deployment is on my desktop PC that I'm running right now. It has a 2070, kind of old, but still does a great job, believe it or not. We have the same cluster secret shared between the 2 nodes right here. Okay. Then we have a unique node name, which is different from the unraid box. We declare that the cluster advertised URL for this node is based on this node's IP address. And this is pretty much it. So I'm just going to go ahead and clear, and I'm just going to go ahead and actually do Docker compose, wait for a minute, and here's our second instance. You know, this is my desktop PC, this is my Unraid box, and this is how things work. Now, if I wanted to, I can go to localhost 5005, log in, and now I can see the Unraid box here as well. Here's how we see models that are on other cluster instances. We see them as available on other nodes, and we can click on this button right here and download them as long as we have the repository information saved, which usually is done automatically. Here's what I'm talking about. This is the repository information. So say, for example, I wanted to download llama 412b, just click on that button and the download just straight up starts. Now I'm going to cancel this because I don't really need it. And the cleanup job, if you have anything displayed in the available models right here, the cleanup job is going to clean that up in a little bit. So I'm just going to close the local node to show you that I can manage any node from any other node. So I'm going to go back to my Unraid box, open settings, choose, this is the null station, which is my desktop PC right now. And now we can see the same stuff. Now, if my desktop PC were using, you know, an AMD GPU with ROCm, you would download a Docker image for it relative to your hardware. Then choose your model right here, and then choose the appropriate Docker image for it. Now we can do share queue with the same model, okay, like we did the last time. Edit this to 1 concurrent and set this to 180 just so it doesn't time out while I'm shooting the video. All right, let's just launch this, and it's going to take a minute because there's a lot of operations that need to happen, and this is running inside of WSL. For a native Windows version, let's just not do a native Windows version. Like, Windows is a pain in the ass to work with, okay? I just had to go and take some coffee, man, while this thing loaded. But anyways, so we have the thing running. So now, because we used the share queue with the same model on both nodes, and we're in cluster mode right now, both have you know, a maximum of 1 active requests, you know, at a time. This is just purely for demonstrational purposes. You can do this if you're batching. You might want to preserve quality across requests as much as possible. So this is why you might do something like this. But yeah, let's take a look at the test script. So I'm going to change up the prompt a little bit here, and I'm going to use a different prompt where I'm going to do like right about 60 words or so. And I'm just going to go ahead and clear this. And, you know, we're still using the GPT-OSS model. We have share queue with same model by name and clustering enabled. So let's just launch the script and see what happens. Now requests are going to come in. 1 is going to get processed at a time. So we have a total of 8 requests distributed, 4 for each node, and they're slowly trickling out. You can see that the 4060 is a lot faster than the 2070, and the queue is slowly being drained while we are getting a response that, you know, as expected, the entry point is the Unraid box, and the request was served by the Unraid box. We saw the first request from my local desktop, and we now see the Unraid box is starting to pull requests from the null station queue, which is my desktop. So this is essentially the gist of how clustering works, but there's even more to it than that. Let's just allow this to finish and allow the second iteration. So this is exactly what I meant by the fact that you can use your older, slower hardware to help with your inference, because yeah, this GPU was slower, the 2070 was slower, but it still took some of the load off of the 4060 in this case, you know, so it helped for the processing of all of the conversations, which is great. It helps you preserve quality, it helps you save some time, and so on and so forth. I would be super curious to find out, like, if you can test with more than 3 nodes, how things behave, you know, in terms of clustering, how everything is being handled. And it is kind of, you know, it's not super responsive right now because there's a lot of operations that need to happen in the background. And we would rather the cluster be more stable than more responsive, essentially. And down the line, we're going to increase the stability and the responsiveness. And also something that we see right now is like if a request is already active on one of the nodes, it's not going to get pulled by the faster node because it's not queued, but because it's already active. Duh. You know, so that this is good to keep in mind because some people imagine crazy stuff. And this is what we have right now. Okay. This is how clustering works. Now, it's very important to note that by default, let me just take a look here at the Docker Compose. The Docker Compose gives you a request timeout default of 300. Now, this might not be enough depending on the model that you're using. If a request is in flight and it hits the 300 seconds timeout for the response to the client is going to get a 504, which is a gateway timeout because of this value. If you start getting a lot of, oh God, if you start getting a lot of 504s in your cluster test script, if these are 504s right here, I suggest to do what I did and just use a higher value, which in this case, I am using, where is it? I think it's 1800. Wait, what? What's going on? Where is it? Yeah, I'm using request timeout 1800 on both nodes, especially for the slower nodes. Like, give your slower nodes more time before they time out. Okay, that's very important for the successful execution of your requests. Okay, so let's continue, and we're gonna do something a little bit crazy right now. I'm just gonna go ahead and stop both of these nodes, and now here's what I'm gonna do. On the unraid box, I'm gonna take this model. It's the OmniCoder 9B, which is based off of Quen 3.5 9B, I think it was. We're going to take this. We're going to set the queue size to 1. And what we're going to do is share queue with the same model. And now I'm just going to take from the cluster load test this alias. I'm going to set an alias for it. Just, I want to show you what this whole thing is about. I'm going to load the OmniCoder 9B model on the 4060 on the unraid box. Just start that up. And while this is loading, I'm going to go ahead on my local PC, and I'm going to select GPT OSS, enable share queue with the same model. Now, these are two different models. And I'm going to do GPT OSS cluster for the group name. Set this to 1, set this to 180. So it doesn't time out, and just launch. Now I'm going to have a little bit of coffee. So the model is now healthy. So here's what we're going to do, right? We're going to keep this in our cluster testing script, and we're going to see what happens now. I'm just going to go ahead and clear this. Remember that we said that we are going to have the GPT OSS cluster for both of these models, which are different within the same cluster. Let's see what happens. We're going to send the request to the unraid box right here. And just send it. What's going to happen? Oh, yeah, imagine this. Let's cancel this out. If you don't specify the cluster name, and if the target environment, which is my unraid box, does not currently run that model already, it's going to start running that model. So I'm just going to go ahead and stop this, get rid of it, because what we should have done in this situation is go ahead and actually use the GPT OSS cluster. Let's see what happens now. We're running two completely different models, okay? Just go ahead and clear it out, run this, and let's see what happens. We see 4 active here, and then we see 4 active here. And now let's monitor, because OmniCoder on the unraid box is a heavier model than the GPT OSS in terms of inference, but it's a larger model and it thinks more. We're basically racing which one completes first. And the prompt that we're using is right about 60 words for each request that is being distributed to the nodes. First request is out, and it was actually served by Null Station, which is my local desktop, which is very interesting. So let's just wait it out and have a little bit of coffee. While we're waiting, like the video and subscribe to my channel, because I need to buy my kitty some cat food, please. Thank you. Hi there. Hello. Oof, kitty here. Kitty here. It's amazing how much hair cats have daily to shed. This is actually quite surprising, because it's the first time that I see OmniCoder be so slow. So for some reason, OmniCoder decided to be kind of slow this time. So we're going to do one more test just to see what's going on, okay? So I'm going to comment this thing out. And right now, we saw the clustering test based off of group name, or rather group alias. Now, what I'm going to do is I'm just going to go ahead and copy this thing over and duplicate this. I don't need to comment that out, but I'm just going to now set the model to OmniCoder 9B. And even though OmniCoder is in the cluster group, let's see what happens. If you guessed that all of the requests are going to go to OmniCoder despite it being in the cluster group, because we specified it specifically by name on that host. You guessed right, and this is exactly what's happening. In this situation, omnicoder is never going to offload to the cluster group at all. And every request is going to be processed on this node by this model. So it's either same model name, or you need to specify the cluster group alias or cluster group name. This is how clustering works. When you set a cluster group name, you can pretty much name it whatever you want, and you can have different clusters on any number of nodes. So go ahead and experiment with that and tell me, post a comment down below of what your experience is, or if you have any sort of an issue, go ahead and click on the link in the video description, which is going to take you to the GitHub page, and post an issue there. I'm just going to go ahead and interrupt this because there's no point in waiting any longer. It's become quite an interesting project, and I'm actually quite happy and quite impressed that people actually like this, because to be completely honest, I really haven't, since this is more of a side project type thing for me, I haven't really invested a lot of time into fleshing it out and just improving the quality of it in its entirety. So here's what the plan is for the future, right? Unless there are some very, very, very big revolutionary type changes, I'm not going to implement new massive features, especially for llamaCpp, because right now it's feature complete in the way that I imagined it to work since the very beginning. In my Gitty, this thing in my private Git deployment, I have a version of llamaMan which is waiting for a merge to the public GitHub with, first of all, VLLM support. So you can mix and match depending on what your environments are. You can mix and match llamaCpp and VLLM, in different places. But also, the idea is that you would be able to cluster VLLM with llamaCpp. Crazy, right? It's kind of difficult to make that happen. And I do have like some pretty big bugs and issues doing that. And it's a big headache, but this is a side project, so don't wait on that feature tomorrow. If you do want to see that feature, please like and subscribe. Post a comment down in the video below if you really want that thing to happen. It is going to happen eventually, but I have pretty important stuff going on in my life right now, so work related especially, so this is not the primary focus. This is already in a good place where I want it to be. When I have time, I'm going to put more effort into code quality, quality of life improvements, refresh rate for the UI, that kind of stuff. Because right now I pressed the stop button, it takes a little bit for it to catch up with the stop command, because we want the whole sequence of events to properly take place before we actually visually update the status of it. And this is pretty much it for now. I hope you like this project. Apparently some people actually really do. We have 2.2k downloads, and yeah, surprisingly good. Check out the other projects that I have and maintain. And last but not least, I'm gonna put in a very small sneak peek into one of my next projects, which is an AI agent that has features that pretty much no other AI agent has. Like and subscribe. Live long and prosper. Peace.